We believe in trust and collaboration and thus follow our mantra, which based on 3 E's: empowerment of end users, enhancement of employee skill sets, and equity to all stakeholders. Now coming to our theme-initiated program, we called it as a Partners in Progress. The strong vision behind organizing such program is to bring eminent speakers of geoscience domain and share their knowledge to the community. The session were designed with an intention to empower students and professionals from the industry and thereby creating a wealth of knowledge for society at large. Now, today we have a very distinguished guest with us, Mr. Jonathan Rood, who is going to give a talk on importance of adopting new technologies in the exploration cycle. He is president and director at Diaz Geophysical, located at Ontario, Canada. He's one of very few geophysicists who has extensive experience in the application of borehole, ground, and airborne geophysical methods to address geological challenges. He has worked in senior management for last 12 years with focus on technology and business management. He is past and induced polarization technology to mineral exploration, oil and gas, and engineering markets. Now, without further ado, we will turn the time over to Jonathan Rood. Please welcome to the platform, Jonathan. We would love to hear from you. Over to you, Jonathan.
Great. Thank you very much, Kanchan, for that kind introduction. I'm very happy to be here and look forward to sharing some information with you. I'm going to try to share my screen.
Yeah, you can, Jonathan.
Yeah, 1 second here.
Yeah, you are a presenter. You can.
Yeah. Can you see that now?
Yeah, we can see that. Yeah.
Okay. So yeah, the title of my talk today is the importance of adopting new technologies in the exploration cycle. And as Kanchan mentioned, my name is Jonathan Rudd. I'm president and CEO of DS Geophysical. And now with some new technologies we're introducing, we also have an airborne survey division, also geophysical. So I appreciate again the invitation from the group and for Data Code for hosting this session. So the motivation for my talk today is to really highlight positive change in our industry and then also to promote learning and discussion. So I look forward to discussion after my presentation. So I just wanted to chat a little bit about the trends that I see in our industry, some of the challenges that we are encountering, and then get down to some of the more specific innovation that we're seeing in the area of geophysics. So the trends, we're seeing a definite call for a deeper exploration within our industry. It's a common theme that all of the near surface deposits have been discovered, and now we have to look deeper. I don't think that's fully true, but certainly the demand is for geophysical technologies that can see deeper. The other demand is for, or trend is that we're seeing a call for more accurate imaging and models. And with that, we're seeing a call for 3D, move from 2D to 3D modeling. And that accurate imaging and modeling really is desired to improve efficiencies in exploration. Geophysics has had a long history and originally very sparse data sets. And now we're seeing much more surveys being done where we're acquiring big data. And of course, that big data is supporting more accurate images and models. And of course, some of these big data sets require the use of machine learning and artificial intelligence to be able to handle the processing of the data, but also the interpretation and integration of the data with geology. And then that kind of follows to the final trend that we see is that there is more rigorous data integration with all these new data sets and these new algorithms, machine learning algorithms. We can do more with our data. We can do more with the various data sets in combining them and drawing better conclusions from them. So those are the main trends that I see. I'm sure there's others, but these are the ones that perhaps affect the geophysical space more than some of the others. So what challenges are we seeing? We're seeing, obviously, in at least in the Western Hemisphere, I suspect it may be the same where you are there. We're seeing a challenge of finding qualified personnel to do the work that is required with a pretty active mineral exploration industry. So finding qualified personnel is a big challenge. Supply chain through the pandemic, of course, there's been major disruptions to the supply chain in a variety of areas. One of which is affecting my company fairly significantly. The challenge of sourcing electronic components and that kind of thing. We're looking at 1 year to 18-month lead times on some of that. So supply chain has been a major problem over the last year. And we anticipate that'll continue on for at least another year. The third challenge, I think, is that there is a lack of experience in the industry. And we're finding that many companies, perhaps many clients, are not making wise choices in terms of selecting their geophysical methods, selecting what parameters to use in doing their geophysical surveys. So that inappropriate survey choice is a challenge right now. And we're also seeing the challenge of how to use the data. We're finding that there are a lot of groups that are mishandling data, maybe asking too much of the data, or perhaps not pushing it hard enough, not using it properly in terms of integration. So we see a fairly significant amount of data that's not being used appropriately. So then on to the innovation. We're seeing, I did these in alphabetical order, numero-alphabetic, I guess. So I'm starting with 3D. We have a lot of surveys that are going into the 3D space. Seismic did it about 20 years ago, 30 years ago, I guess now in the 90s. And now we're seeing induced polarization, which is one of the methods that we do now, going 3D, and we expect that most IP and resistivity surveys will be 3D in about 5 to 10 years from now. As I mentioned, artificial intelligence, machine learning, big data, there's a lot of growth and progress in those areas as we're seeing more and more use of these algorithms and technologies in the processing of the data, the inversion of the data, and of course the output of the and the interpretation of the data. I think that's also very important. A third piece is diamond nitrogen vacancy magnetometers. That's an emerging technology. Lockheed Martin started the development of these, the research on these. But we're seeing more and more groups that are getting into investigating the possibility of using these nitrogen vacancy diamonds as magnetometers. A very promising field. Full tensor aeromagnetics is relatively new to our industry as a whole. There's one major mining company, Anglo-American, that's been doing it for 10, 15 years now. But this technology is now becoming available to the general industry. So full tensor aeromagnetics. And then ground penetrating radar. We're seeing great progress in that with Jan Franke's group in sort of enhancing the depth capabilities of GPR in the application as well. We're seeing a lot of growth in the power available. So again, this speaks to the need for depth, deeper exploration. There's been a lot of research and development into developing higher power transmitters, so the geophysical sources. And with that, of course, comes a higher signal to noise and a greater depth penetration. Muon technology. I'm actually currently at the office of a company that has developed the Muon technology, and it's starting to enter into practice in our industry. So imaging dense and less dense features using these small particles called muons. Passive airborne electromagnetics has been around for about 15, 20 years with Geotech ZTEM system, but there's been a lot of growth and development with some new systems being developed for that application. SQUID sensor technology, certainly on the ground, it's really growing very rapidly in use because of the high sensitivity of these SQUID sensors. So for ground EM surveys, more and more SQUIDs are being used. Again, that speaks to the need for the ability to image deeper. And now the SQUIDs are being used in airborne technology. So up to the full tensor aeromag up here. The SQUID sensors are being used for full tensor aeromag. And I'll be talking a little bit about that later. And then finally, of course, the UAVs or drones or whatever you want to call them. So that we're seeing a revolution of the use of UAVs, and we're very interested to see how that progresses. So I'm just going to give you an introduction. DS Geophysical is my company. We've been around for about 8 years, and I thought just a couple slides to introduce you to who we are and what we do. So the company was started 8 years ago, and our main purpose is to develop new innovative technologies. So we don't want to build technologies that are already out there. We want to build technologies that are better and significantly better. And so we've created a patented 3D Earth imaging. So this is the SQUID sensors and the ground IP and resistivity systems, and I'll talk about those. And then we've developed a 3D processing, 3D data processing, and 3D inversion system that allows us to handle these very high volume data sets. And then we actually do a lot of our own development. So we design and manufacture our own equipment, which gives us great flexibility. And of course, we actually do our own surveys. So we do surveys around the world using our equipment. And then, as I mentioned, we call this our cloud solution for the processing and inversion of our data sets, DS Caravel. So again, this is the ability to handle very, very large data sets and to produce these high resolution and rich, accurate data 3D models. And we have a very strong a pipeline of new technologies that we're developing, QAMT, some airborne technologies, and some other ground technologies as well. So just a brief introduction to who we are. Our head office is in Canada, central Canada, Saskatoon. We have other offices, and we've got presence in other countries, in Chile and Mexico and the USA. But we've done work right around the world, including in India. This survey was done in Rajasthan, in the northwest for Zawar mines, and so we were happy to be able to work there. So we are an international company, and we hope to be back to India soon. So I'm gonna just by way of sort of an example of what new technology can do, I'm going to just introduce you to this technology. This is a ground 3D, a direct current induced polarization system called DS32. This system was developed 9 years ago and went into production, into use 7 years ago. And it produces very, very high volume data, and it also produces high signal to noise. So again, addressing the the call in the industry for high resolution and good accuracy, and also great depth search. So I'm going to get into some detail of what the system is. We have our individual receivers here, and we would lay them out across a survey area. This survey area could be small if it's an engineering scale survey, or it could be large, hundreds of meters separation, if you're looking for porphyry or target deposits. And then we connect all those receivers up with what we call a common voltage reference wire. So it's just a wire, thin wire that runs between all the receivers. And then that allows us to generate dipoles. So we're subtracting the response from all these receivers, and we're able to build a lot of dipoles from a relatively small number of receivers. So this speaks to the very high volume of rich data that we're able to collect with the system using this methodology. So this CVR method is patented, and it's the leading IP technology in the world today. So what does that do for us, that technology? It provides high signal because we have a high power transmitter, the GS5000 transmitter. This transmitter is 25 kilowatts, 5,000 volts. And then we've got low noise receivers because we have what common mode rejection in the way we acquire the data. And then we actually are able to generate small dipoles and large dipoles using our CVR methodology. So that we call that multi-scale. And so again, very big data and rich data. So it provides the ability to get high resolution, which is important in areas where you've got complex geology, and the depth, as mentioned, with the high power transmitter. So the big data is very important for areas where you've got lots of culture, perhaps mining operations, or you're close to communities, because if you have lots of data, you can reject the data that's not so good because it's being contaminated, and still be able to image accurately. So it's in the top right here. This is one of our data sets from a survey we did in Eastern Canada. This is an example of a survey we did in a very challenging environment. Because this technology is very lightweight, mobile, we were able to get into some fairly rugged environments. So this is one of our operators with the equipment climbing the side of a mountain, and that was on this survey here. So you can see the terrain, the contours from the mountain that we're surveying on, and then this cloud of dots is the actual data that we acquired. So there was about 70,000 data points acquired during that survey. And that model, that data, of course, is modeled up using our 3D inversion routine, and it generates a very highly resolved model of what's going on in the subsurface. This is the resistivity model for that survey area. And then this is the chargeability. So 2 data sets from that survey. And we're seeing east-west geology and structures, but also deeper northeast trending features as well. And if we look underneath at this data set, at the resistivity data set, we can see that the survey is actually imaging these veins, they're epithermal veins, which are in different directions. So it's imaging in great detail what's going on in the subsurface because of the high resolution and the high volume data that's used as input. The client drilled this project. They didn't get as much gold as they hoped, but technically all of their drill holes hit, and they're now exploring deeper for a porphyry target. So here's the IP chargeability, deep IP chargeability feature that they're now targeting for porphyry mineralization. The second example, just again to demonstrate the advancement that new technology can bring. This is a survey also in Western Canada, where a survey was completed a few years ago by an older system. And you can see on the right image here, The old survey is on the right 1/3 of the property area. You can see it's a relatively low resolution results. And then on the left-hand side here is where we completed our new high-resolution survey. And so you can see just the improvement in terms of the detail, the resolution, and the interpretability of that new data set. So their geophysical target, they're looking for coincident so resistivity and chargeability highs. So they were looking for silicified alteration and then sulfides associated with that. And they will also are correlating their magnetics. So this is the magnetic map with the resistivity and the chargeability. And they found that there's a very strong spatial link between these anomalies, and they've observed bedrock alteration patterns and anomalous epithermal pathfind or element concentrations as well. So they're using all of these data sets. So the geochemical, the magnetics, and the resistivity and IP data sets to target. And they're having results, good strong results. You can look on their website, Thesis Gold, to show the very good success they're having in following up these anomalies. In this case, they're looking for resistive features. So this blue is resistive, and the red down here is the chargeability. So it's a resistive, coincident resistive and chargeable feature. And these dotted lines are the interpreted fault structures, which are controlling the mineralization. Again, this one here, a resistive feature with a chargeable source proximal to a structure. Second example, this is from a few years ago in a uranium exploration environment. I know you have uranium exploration going on in India with AMD. And this survey was done over a known deposit. So the red polygon or volumes here are the known mineralization, and the gray is our survey results. And we can see that there's a general correlation between the two, although our survey is responding to the alteration associated with the mineralization, not the mineralization itself. So it's not a direct correlation. But the alteration is an important pathfinder to find the uranium mineralization. And so as a result, they identified this strong potential alteration anomaly here, about 400 meters from their deposit. Actually, it was more than 400 meters. It was about 800 meters, I think. And so they drilled it, and they found some very strong anomalous responses. So they made a new, what they're calling South Arrow deposit as the result of our survey. So they have some discovery holes, and so we're excited to be partnered with them on that discovery. This is an example from a recent survey we did for a company called Ivanhoe Electric. It's a porphyry target and known mineralization from a long time ago, and they've come back on this property and done a new survey. The reason I'm showing you this particular image is that they're looking down, if you can see the scale here, they're looking down more than a kilometer. So this IP resistivity survey is imaging down about 1.3 kilometers, which is really not normal. Normally limited to about 600, 700, 800 meters. But we're seeing down here about 1.3 kilometers with the high power and low noise character of the system. So they're very excited to see these new anomalous targets, which are sitting below their cover rocks, and also the anomaly to the southwest here. The second technology I wanted to chat, so just demonstrate as another example of innovation and the effects that it can have, is the QMAG-T system. So it's on the right here. It's an airborne towed bird. So the helicopter has got a rope underneath it. It's towing this, we call it a bird, and the instrumentation is contained inside the bird. And there it is on the left in flight. It's the sensor system is cryogenic, so it's liquid helium, very, very cold, 7 degrees Kelvin. And the helicopter, as I mentioned, is a towed bird. We just hook our system onto the helicopter and then we can just go flying. So very, very simple to operate. 270 kgs for the whole system, so relatively light. And we don't have to put an operator or a second person in the helicopter. The pilot can fly it on its own. So this is the bird here with one of our operators, and we're refilling the cryostat with liquid helium. So this is a large container of liquid helium, and we're transferring it from that into the sensor cryostat in the bird. We have to do that every 3 days. So what is full tensor magnetic gradiometry? So full tensor mag is the ability to measure the directional information about the magnetic field. Most, I would say all, magnetic surveys, if you say I want an airborne survey or a ground survey now, you're measuring the total field. You're not measuring any directional information. You're just measuring the total amplitude or the strength of the magnetic field at each location. This system is actually measuring 9 directional parameters. So it's measuring the second order tensor of the magnetic field. So visually you can say, okay, well, if your magnetic field is given by a vector, this is telling you how that vector is changing in each direction. So not only is that vector, you're defining that vector in the X, Y, and Z, but you're also saying how is that Y component varying in the X, Y, and Z, and how is the Z component varying in the X, Y, and Z. So that's what the second order tensor means. So there's 9 tensor components. Of those 9 components, some of them are the same, as you can see. The BXZ and the BZX are the same, and YX and XY are the same. So there's really only 6 that are different, right? These 6. So that's what we deliver. We measure 9, and then we deliver the 6 independent tensors. So as you can see, a total field survey would be delivering just a single value over an anomaly. This particular anomaly is a synthetic cube that's sitting in the ground, and this is what you'd get with a normal total field survey. With the full tensor mag gradiometry survey, our system is called QMAG-T. You're getting these 6 component measurements over that same cube. So you can see you're very clearly defining the shape. You're defining the north and south edges. You're defining the east and west edges, and then you're defining the corners, and you're defining the XX and the YY, which are basically the roots of the ZZ component. What does the data look like? The raw data looks like this. It's measured on 6 SQUID gradiometers, and then it's processed. They call it balancing to split it out into the individual tensor components, and then we rotate it into a proper coordinate system. So raw data balanced and processed. So you can see it's a fairly rigorous processing flow. So instead of taking one measurement, so you can see this is a single line or a flight line of data across a nickel deposit, actually. Here is what you would get with a normal total field survey, which is what most people do when they do mag surveys. So the green, you're just getting the one measurement. With the tensor, you're actually getting 6 measurements. You're getting the 3 on the top panel, you're getting the 3 on the second panel. So you can see the extra resolution and the information that's contained in all of these tensor components. What does that look like? This is a survey done in South Africa for looking at the reef, looking for dikes that are going through the reef for platinum palladium mineralization. This is a survey that we flew in Western Canada looking for gold. And this is just a comparison of an earlier total field survey and then the BZZ component, just one of the components of the SQUID sensor. You can see the higher resolution that you're getting with the new technology. Quite a difference. And then, of course, the difference in version. A rougher, coarser data set like the total field is is going to give you a much fuzzier, less defined inversion. So this is a comparison between a total field intensity inversion and then a FTMG survey. This is another example of a QMAG-T survey. This is for Vale. So they're looking for nickel in this particular area in northern Manitoba, and they're looking for high tenor nickel, platinum, palladium, or PGE, platinum group element deposits. And so on the left is a total field, what you'd get with a total field survey. And then on the right, you can see the 6 tensor components from the survey that we flew. I think it's just a higher level of detail and resolution in the SQUID tensor data set. This is an example of how you can process the data. This is processing done by Intrepid. They have special software designed to process these tensor magnetic data sets. And another group called Tensor Research in Australia has also developed a lot of software for the processing of these full tensor magnetic data sets. And so you can derive a lot of very useful information, in this case, susceptibility and thickness of the body and how deep the sources are. And you can use artificial intelligence sort of in a very beneficial way for the processing of this data. And they've classified potentially remanently magnetized sources in the bottom right image here, as shown in yellow. In the top right, we can see the depth information that's available. You can see very accurate depth interpretations and obviously potential faults and breaks because of the varying susceptibility across these features. This is an example of a comparison between total magnetic intensity inversion and the QMAG-T data inversion. You've seen these sections through the inversion model, but on the bottom you can see the 3D ISO body views, so full resolution on it. This one, I can get it going as well. So you can just see the added resolution you're getting in detail, particularly in the near surface with the QMAG-T data. Mira Geoscience is a consulting firm that does a lot of work with constrained inversion. So I'm sure there's many groups that can do that. This is just an example of how they've taken this particular data set, added some geologic constraint, and created a model which is more unique. It has less degrees of freedom, of course. And so these data sets are, because they are so rich, you can create some very, with some sort of a priori information about the geology, you can make some very accurate and compelling models of what's going on before drilling. Here's an example, quite an interesting one, actually. So this is a survey we flew in an area where we have these diabase dikes running through, so they're magnetic highs. This is the total magnetic intensity image. You can see that you've got these 2 dikes that are coming down through. You can see the evidence of maybe a third one coming down through here, and another one coming down through the corner. And but then when you do the QMAG-T survey or the full tensor survey, in the BZZ component, you can actually see these 3 dikes very clearly, with higher resolution, and this 4th one here. But then as you look at the other components, you actually start to see some complexity. What's going on with the BXY? All of a sudden you see that dike, which is coming down here, is changing polarity in that intervening section. So what's going on there? Is there a rotation of that section? Is there some remnants that's different there? So you can see that it's not just a simple case of a dike that's changing direction. It's actually changing magnetic character as well. So the tensor data is very important for to understand fully what's going on with your magnetic sources. And of course, modeling of the tensor data, which can be done in 3D with the codes that are available now, facilitates that as well. So, we look at what, how does this help in application? I've sort of demonstrated that, this new type of tensor data set will improve resolution and detectability of weak sources because they're very, very low noise SQUID measurements, right? And it provides higher spatial resolution. A paper written in 1990 indicates a 2 times improvement in resolution. As I mentioned, you have a much better chance of resolving your remnant magnetization when you have the directional information. That's kind of a logical outcome. And in fact, the ability in low latitudes, magnetic surveying can be very challenging to interpret, particularly with north-south geologic features. This system provides advantages in those environments, and actually is able to resolve north-south features much better. And then, as I mentioned, improved geologic modeling. So where does this apply? This technology, we've done a lot of work already in kimberlite mapping. De Beers is using this system as well for their mapping of potential kimberlites. And another application is in ultramafic intrusion, so nickel exploration and that related mineralization, simply because there's a lot of remnant magnetization at the margins of these intrusions where the mineralization tends to occur. And that can make drill targeting very, very difficult and inaccurate. So the directional information allows you to resolve what's going on in these environments much better. Complex structure with this extra resolution and the directional information, you can resolve D1, D2, D3 much better. Iron ore is another application, and as I mentioned, low latitude mapping. The second system, which we're just introducing, it's also a SQUID-based technology, and this is a natural source airborne EM system. So this would compete against a ZTEM system or a mobile MT system. It's using the Earth's atmospheric electrical energy as the source, and we're measuring the Earth's response to that. And so it's again relatively lightweight system, but very, very high resolution. We're measuring 3 components rather than a single component as other systems do. And so we're able to provide a much more accurate and much more resolved image of the Earth with the system. Just a quick example. I don't want to I think I'm getting close to my time here. But a quick example from that system, passive system. So this is in Germany, a survey that was done, a 3D model of the geology from that. If you look at that in plan view, you can see that on the right is the SQUID QAMT system results, and on the left is a survey flown with a helicopter frequency uranium survey system. So you can see the resolution is actually quite good with the SQUID passive system.
Jonathan, if you have something to speak, you can carry on with the time. There is no issue. We can.
Yeah, I think I'm pretty close. I'm pretty close to the end anyway. So
okay, fair enough.
Certainly happy to. Yeah. So yep, there you go. So right at the end here. Your timing is good. So yeah. So just in conclusion, we're convinced that innovation is core to the future of our industry, particularly as there's great demand for the battery minerals, copper, nickel, cobalt, lithium. There's going to be great demands and a lot of money flowing into the industry, and we're going to have to figure out ways to explore more efficiently, more effectively, and so innovation is going to be driving a lot of that improvement, of course. And big data is here. More and more we're going to see larger data sets, and so we have to embrace it. I think there can be a tendency to kind of say, "Oh, I don't want to deal with all that data. It's too much. I'm just going to get rid of half of it," or and that's happened to some of our clients. Is that some of them can't handle the data, and so but we have to embrace it because there is value in all of the data that's available. So don't throw it away. And then just an encouragement to explore the new technologies that are available, the ones that I mentioned at the beginning. I've given a couple of examples of new technologies. There's lots more out there. So get online and explore, find out what's available out there. And then the final point is that with any of these new data sets, you have to do a good job of integrating. So we do not claim that when we do a survey, you only need our data to find what you want to find. We always encourage that our data set be integrated with other data sets, magnetics or geochemistry or geologic models, and so that's absolutely critical that the integration take place after. But in the end, if you do that properly and you use the right data sets, you can add so much value to exploration programs. So I think that's it. I do want to thank you, all the companies that sort of allowed us to show their data, and I want to thank you for your kind attention.
Jonathan, at the onset, it was good presentation. I have one of your users, Shivani. Shivani, do you have any questions for Jonathan?
So I'm not.
Yeah, Karunakar has a question. Yeah, go ahead, Shivani. You have anything? Okay, Karunakar, you can ask the question. Karunakar, you can unmute and ask your question.
Yeah. Hello.
Yeah,
Hello.
go ahead, Karunakar. Yeah, go ahead.
Thank you very much, Janardhan. I think it's a wonderful presentation and a good learning for me for the new technologies, whatever is happening. It's a very quite good information, like whatever is advanced geophysics. And my question is, in India, having a lot of cultural noise and all, like a lot of high tension power lines and a lot of noises. So will this SQUID system, airborne system, will be helpful? Like because in India a lot of population and cultural noises. So how this is useful? Like, have you tested anywhere like with a cultural noise?
Yeah. So as I mentioned, with our ground IP resistivity system, we've done a fair bit of work in areas where it's noisy, in mine environments, also in areas where there's, cities, towns, homes, power lines, and that kind of thing. And generally, we collect enough data because we are collecting high volume data to be able to overcome those noise sources. There are some environments where it's problematic, but because we're collecting so much data, we're generally able to sort of get rid of the bad data, right, or the noisy data, and we're left with enough to do some good modeling. On the airborne side, so the one system is a magnetic gradiometer system. It's pretty impervious to noise sources. It has natural filters of the normal sort of main power frequencies, and because it's measuring the magnetic field and not an electromagnetic field, it's able to survey quite effectively in those environments. The passive system, we haven't done a lot of surveying with it yet, but we do anticipate that's going to be a problem. The QAMT system, we do anticipate that we will have a challenge in noisy environments, and it really does come down to the character of the noise. If it's a very strong noise at a very particular frequency, then that's something we can deal with, right? Because we can filter it out. But if it's dirty noise in a way where you've got a sort of a broadband response or a number of different frequencies, then of course it's going to be more difficult to deal with. So a bit of an unknown on the passive EM system that we're developing. Hopefully that's answered your question.
Yeah,
Jonathan,
thank you very much. And my second, one more question is on DIAS 32 is how much the transmitter power you use for these DIAS 32 systems? What is the power of transmitter?
Yeah. So the actual transmitter, the individual transmitter is 25 kilowatts and 5,000 volts. But we're able to put 2 or 3 of them together, so we can stack them together. So that gets us up to 50 and 75 kilowatts. And that's at the 5,000 volts. Yeah. So and 20 amps is the limit. We've never kind of run up against that. Normally you can't get that much current into the ground, even in conductive environments. So, in areas like Western Africa, in parts of the US, in Mexico, when we do surveys there, we're normally putting 2 transmitters together and operating at the 50 kilowatts.
Good, great. Thank you very much.
You're welcome.
Jonathan, regarding the tensor magnetometer, I mean, because there have been some ground-based systems are also being developed, as you must be aware about. So how do you compare what you have and what should be the approach? Because that's something new for Indian setup. So how do you think that we should look at it?
We introduced it about 2 years ago, or 2.5 years ago, just when the pandemic started, right? And so it was lousy timing, and so things went slowly. But since the pandemic is finished, we've had a number of major companies. They know that we have the system. We've let them know it's a tried and tested system. So Anglo American has been operating the system for 10 years, right? And with De Beers and their Spectrum Air group. And so we've done surveys in nickel environments, in diamond environments, and in gold environments. And so these companies are going in, they're doing a test, they're comparing it to their existing data. And in every case so far, they've said, great, let's fly the whole property, right? Because it is that much better in terms of the resolution and the information that's coming out. So it's a step change. And there's been talks at the PDAC conference over the last few years. Joel Jansen spoke, Wayne Stesnowski spoke maybe 3 years ago. And but they're all predicting that this technology ultimately will become very widespread in widespread use in the industry. It'll take a while for the industry to come to that, but over time, we're pretty confident that it will become very common and accepted, and the value will be seen in the industry. So typically we'll fly our surveys at a 75 meter, 50, 75, or 100 meter spacing. And we're flying at 30 to 40 meters elevation, and that's pretty appropriate. It's on a helicopter now, so it's more expensive, right? Ultimately, the system will be put on a fixed wing, and that'll bring the price down, right, for areas where it's not too rugged. Yeah.
No, but the challenge which I know of India flying, whether it's a Airborne or it's a fixed wing, it takes a lot of initial challenges of getting clearances and technical stuff. So how do you advise? Should it be look at can this be, you look at drone kind of a system, which would be the platform for such systems going forward, or would it be possible to have ground systems which can do short, small projects, small areas?
Yeah, so I mean, I've got my own views on the drone systems. Right now, it's a fairly heavy system for a drone to carry around, right? And it's also very expensive. So the drones aren't that reliable right now. So we're reluctant to put the cryostat, onto the with all this expensive under a drone, which again is they tend to crash too often, right? So maybe in a few years, 5 years, 6 years, there might be a bit better stability in that area, and drones would make sense. But for now, we don't really see that as an option. But yeah, ground is expensive, right, for the coverage. Drone, yeah, I suspect you'd want to get your government interested in trying the system out and bringing it over there, right? And do some test surveys, and then the system's there, and you can do other work, right? I think if the government understands the value of it, then perhaps, right?
Shivani has a question. Shivani, go ahead. You can unmute yourself and speak about your query.
I think you're muted.
Good morning,
Shivani.
Jonathan.
Hi, Shivani.
Can you hear me now?
Yes,
Yeah,
I
we can
you.
hear.
Okay. So I have already put my question in chat. When on a IP chargeability section where we try to interpret, we see some parabolas. It seems like a feature which is which looks like an anomaly. So I just wanted to ask whether it is due to current flow limitation or it is a real feature. It seems like the anomaly is open at depth.
Yeah, that is kind of tough to say unless I can see it. I'd be certainly happy to take a look. We can get Charlotte to take a look at the particular anomaly that you're speaking of. But is it one of the ones that I presented, or something in your own data?
No, I'm talking about some Java sections I have seen in the past.
Sure. Yeah. Unless I see it, I really can't tell. But happy to talk with you about that. If you wanted to show me exactly what you're referring to.
Okay.
Yeah.
I'll
We're
share
happy to
my
look
question
at it.
through email then.
Yeah. Sure. Yeah.
Thank you.
Yeah. You're welcome.
Jonathan, at the onset, I would like to thank you for sharing this time at late evening for you. Probably being not much of audience could come in because of early hours in this, but generally we are having quite a good audience. Avani sir, he's on your side of the continent. Avani sir, do you have anything for Jonathan?
But just Jonathan, I just came from a conference, or it's a kind of fast edition small meeting, or you can say conference, actually held in Calgary, and one of the presenters were the energy minister from Saskatchewan, and of course he talked a lot about the potash, and of course potash and uranium, and I was pleasantly actually surprised to see that you are from Saskatchewan. It's a very wonderful. Saskatchewan is a wonderful city. The question is actually, I think you touched on that. Just post-pandemic and time and given the demand for for specific commodities, right? We group it as critical minerals, battery minerals, and we talked there actually in that group. They said it's electrical minerals. It's the same group of metals we're talking about. But do you see that there's a peak for any specific commodity other than like lithium, copper, and cobalt? Any other specific metals or commodities that you are seeing a good demand for your application?
Yeah, so I mean the one that we're seeing the biggest demand for is copper. I mean it's going to be, and it's a battery metal because you need a lot of copper to conduct, right? So there's going to be massive demand for copper, and we're doing I would say 75% of our work is copper related, and then the other one would be nickel. Nickel is also very important. So
what about potash?
Potash is a fertilizer, so it's critical, obviously, for agriculture. And
But not the reason
not
actually,
for-
Jonathan, the reason, sorry to cut you off. Actually, the reason actually potash came into picture is the LFP technology that is coming, and there's a specific type of potash we're talking about, a particular type of ion of potash that we're talking about. And then in that discussion, actually, I challenge the audience, like, you cannot forget the aluminum and steel in the mix. And if we're talking about steel, you have to think about lead and zinc and chromium. Without that, steel is useless. You just cannot use it. And that kind of for the discussion, I guess what we're leading is, Jonathan, I guess, prepare yourself for a huge demand just post what do you call it, PDSE in 2023. We are kind of gearing up towards that. One of those days I may actually stop by at PDSC, say hi. Thank you, Jonathan. It's a wonderful presentation. I was listening.
Yeah, absolutely. Look forward to meeting you there.
Sure.
We'll have,
I'm in
we'll
Salt
have
Lake City,
some-
actually. We're in the same time zone, probably.
Yeah, that's good. Yeah, I'm actually in British Columbia right now, but I'm just visiting.
1 hour difference then. Yeah.
Yeah. Okay.
Okay.
Good.
Thank you.
Yeah, nice to meet you, and look forward to seeing you. Okay, is that all the questions? So if that's all, I think I will say bye, because it's quite late here, and I appreciate again your kind attention, and hope you all have a good day. Thank you so much.
Thank you, Jonathan.